This time, as I promised you, we're gonna build something with Rust. And I made up my mind about what exactly I want to build. And I came up with a very simple tool, which is still complex enough that we can learn a lot from it, which is a line of code counter. So what does a line of code counter do? Well, I envision this to be a command line tool for which you either input the files that you want your lines of code to be counted, or you input a directory and it will automatically look for code files, and then in the end it will tell you something like, okay, in this file you have 18 lines of code, in this file you have 115 lines of code, and so on. So the usage that I envision will be the following. We will call this tool LOC counter, and then you will have 3 optional flags. And one optional flag, or actually they're not optional, you have to use some of them, otherwise the tool will not know what to do. But the first flag will be a -f, and then you can write all the files that you want. For example, src/main.rs, and then you can have a second file, for example, src/test.rs. This is where you provide your individual files. An alternative usage would be you just provide a directory, which could be .src, and then you provide file extensions, which will be with the -e flag. And here you would, for example, have rs, or you could specify multiple of them. So you'd say maybe you have some JavaScript files as well, or some HTML, and you could do it like this. So an example usage would be LOC counter, and then either have this flag to directly specify the files, or alternatively, you would want to have a -d and a -e to specify a directory and some file endings. So let's start. This is a blank sheet, and for blank sheet projects, depending on how big they are, I would either write a complete architecture, which would be way overkill for this project, obviously, or I would at least sketch out a bit what we want to do. So the first step should obviously be we need to read the command line argument. So this is our first step, the command line args. The second step would be we have to check if the files are provided with -f, whether those files actually exist. I mean, could be a typo in there by the user. And if we have the second usage case with the -d and the -e, we would have to walk this directory to find all the files that have either of those file endings. So the second thing would be we have to create and verify a list of all files. Third step, we have to do the LOC counting. And in here, we have to read each file to, let's say, a vector of strings, which are the lines. And then we have to check if it is a code line. Well, why do we need to do this? I mean, the rules for it being a line of code are quite arbitrary. I guess you probably would agree that an empty line is not a line of code. But what about a line that looks like this, just an opening curling brace? And would this be a line of code? Maybe, maybe not. I mean, it depends on your definition. But we will have to implement some rules which will determine whether a line that is found in one of our source files is actually a line of code, or whether we're gonna disregard it. And in the end, I want to print an output statement. So print the lines of code to the terminal. I think those are the 4 steps that we will need to take. And I guess that's a good way to get started. So I did some thinking and some preparation of this project ahead of time so that I don't waste a lot of your time. So just keep that in mind. I'm not inventing things on the fly, but I'm having some loosely guided structured code that we'll be using here. So the first thing that I learned from Luca Palmieri's book, Zero to Production, is that when you can externalize some functionality, when you can group that into a module, you should definitely be doing that. And I think we have 2 very clear tasks to do here. One is concerned with point 1 and 2, which is reading those commands from the command line and finding a list of all files. So this is kind of your configuration, I would say. And then you have the second part, which is the actual countings of lines of code. And you could, or we will externalize this into a module because this could be reused in some other project, okay? This is just very generic, reading command line arguments and creating and verifying a list of all files. And then the second functionality that is totally decoupled from the first one would be the lines of code counting, because in here we just expect that we have a list of files that are already verified to exist, and we're doing our second task, which is deciding whether a line is a line of code and whether we can, and summing them up, basically. So what I'll be doing here is I create a new file, which is config.rs, and in order to be able to use this, let's leave this comment on top as a reminder of how we want everything to work. In order to use the module, we will now create this or define this module config. And on top of that, we will use from our own crate, the config, and yeah, we will have, I didn't already code this, but we will have a class in there or a struct called configuration. So to start off here, we will have a struct and we'll make this public so that we can access it from main.rs. Struct configuration. And this struct will have all the configuration in there. So we have 3 possibilities to configuration. One is providing the files directly, and the other one is directories and file extensions. So we'll just save all of this. And on top of this, you can, for example, if we had a test folder, you can provide multiple files separated by a comma. You can provide multiple directories separated by a comma, and you can provide multiple file endings. So all of this can be vectors of strings. So we'll have our file extensions, which is a vector of string. We'll have the file names, which is a vector of string. And we will have our directories, which is also a vector of strings. Pretty straightforward here. And let's do one thing ahead of time. I'm sure we'll need to print the configuration for debug purposes. So we will derive debug right away. So we'll have that out of the way. And all of the other functionality, like parsing the input arguments, finding all of the file names, etc., we will have in this input block configuration. Okay, so far so good. We've got everything set up. Now, what I want to do next is I want to have a kind of a constructor, so to say. You know that constructors are not strictly special member functions. There is just a convention to call a constructor new. So we'll have this public so that we can access it, and it's a function new. And from what we want to construct it is probably the command line arguments that are given by the user. So I'll call this args. And we want to take this in as a vector of strings. And as this should be used as a constructor, we have to return a configuration, which is aliased by self here. And in order to start things off, we can just create an empty configuration, meaning that all of our vectors are empty. I will call this config, and this is a self, so a configuration. And we'll just get some help from VS Code here to make this a bit quicker. So all of these are empty vectors, and because we defined our configuration on top, we already, or the Rust compiler already knows that this is going to be vectors of strings. And in the end, we need to return our config so that everything works out well. I made this mutable because, of course, within this constructor, within this new function, we will have to add into these vectors. So we'll need a mutable version of our configuration here. So when we're thinking chronologically, what will need to happen first, we will need to read the command line arguments, which is actually really, really simple. There is a module that is called stytenv. Stytenv allows you to access environment variables and command line arguments. So the first thing we'll do is read those command line arguments in the main function. And the way you do this is env args, and this can be collected into, well, into what? If you do not provide the type that you want to collect into here, the Rust compiler will be confused because it doesn't know whether you want to collect this into a set or a vector or whatever. So there's two ways to specify this. One way is to give this args a type. So for example, we could say we could say args is a vector of string, and now the compiler is satisfied. Or you could specify the generic type that you want the collect to have, which would be a vector, and you don't even need to specify here that it will be strings because it knows that from args. So specifying both this and the vector of string here is a bit overkill. I think that defining the type on the variable is a bit neater. It looks like cleaner syntax, but like you do you. It's your choice at this. And the next thing is we need to hand over the args to our config. But before we do this, let's just see what the args look like. So we'll have a print line of args here. Let's do like this. And we need a new terminal. And we'll do cargo run without any arguments. Okay. Of course, we get some warnings because we have unused variables. We won't care about that at all here. The only thing that we really care about is to see our args. Okay, in this case, args is a vector of string, and it only has one string contained in it, which is the path to our executable. So that won't help much, and we definitely don't need this for our case. So if we do cargo run, and we'll try to, for example, give, let's just copy from here. Give the arguments that we would like to have. -f, we forgot the equal sign. Then you see the following error, unexpected argument -f. Because if you give this argument like this, this will be an argument or a flag for cargo. And cargo doesn't know what to do with a -f argument. So the way we have to do this, after run, you have to put a double dash and a space, which means all the flags that are before this double dash and the space will be flags that apply to cargo. And everything that is after this double dash are flags that will be handed over to our program. So if we'll do it like this, we can see, okay, now we got two args, the path to our executable again, and we've got the -f here. Very nice. Let's do a second test. Let's just take our second execution example here with a directory and file endings. And we'll see that it basically splits the arguments at a space, which means that we get the -d here as one argument and -e as the other. So we kind of know now how this works. So why don't we write a member function in our configuration, which does the parsing for us? So this does not need to be public. Why? Because I want to call this function in our constructor. It doesn't need to be called from outside. So I'll call this parse args. And because we want to generate some strings that we will push into those members, we need to have a mutable reference to self, and we'll have our args as a vector of string, as we saw, and we won't return anything here. So let us see what we can do in here. We get our args as a vector of string, which means we'll probably just loop over our args. Also, we will assume that we only get the actual arguments, the actual flags, and we will not get this first argument, which is just the path to our executable. So let's loop over everything for arg in args. First thing we could do, we could just print it. I'm a big fan of having a lot of debug statements until you really know what to do and you really know how the flow of your program is. And then what? Well, we definitely need to work on a per character basis here, because we need to make sure that the first character is a dash. We need to make sure that the third character is an equal sign. Otherwise, the syntax isn't correct at all and we'll probably error out. And then we will decide based on the second character what to do. Well, is it a D? Is it an E? Is it an F? And the way we'll do this here is I'll convert the string into characters, arg.chars, and we'll collect this in a vector of characters. So let's say of character. Why do we use chars versus byte? Well, byte is the more efficient version to represent a character because it only needs a byte, obviously. But the problem with that is it can only represent ASCII code, or ASCII encoded characters. Meaning that if you're on a computer that utilizes, for example, the German alphabet and has any umlauts in there, or you have Arabic characters that will present your paths, then byte will not do. In fact, you need chars because chars is UTF-8 encoded characters, which means that we have some overhead when we create them. We need to make copies because it's a lot more effort to parse characters in UTF-8 than it is to do in byte. Because in UTF-8 you don't really know how long the character will be. In ASCII you know it's going to be 8 bytes, 8-bit. But as I said, for obvious reasons, we want to allow to have UTF-8 characters and not only ASCII characters in our path and in our file names. And now we can check if characters at 0 is not equal to the dash, or if characters at 2 is not equal to our equal sign, and now we know we can only allow 3 letters, so I'll just make a collection of those 3 letters, which is a D, an E, and an F. These are our 3 allowed letters. And if this does not contain our characters at 1, which is probably the letter, then we really have no way to recover here, right? I think if the usage of our command line tool is not correct, we will just print a kind of a help page or a tutorial on how to use it, and we'll error out. So we do e print line. Why e? Well, e print line will print to the error console rather than the normal console. And for example, if you do something like LLC counter and you give some argument, whatever, and then you forward that into a file, for example, log.txt, everything that is written with print line will be forwarded to this file, but everything that is written to the error console will instead be shown on the console, which means if you would have print line only here, and the user forwards everything to a log file, then all the errors will also be forwarded to the log file, and the user has no idea that the program actually failed. Whereas if we do this with ePrintLine, then the error messages will always be shown to the user, and he knows that, that something failed. So what do we do here? We print error, and whatever the argument is that did not match is not a valid configuration argument usage. And I'm just basically copying from my template here. So specify a single, or a single is basically wrong, one or more files. And we'll do this with -f. -f is equal to path to file.rs, path to other file.rs, for example, like this. And by the way, this backslash at the end of a line will denote a multi-line string in your source code, in the Rust source code. And the other one will be specify a directory alongside file endings. This will be -d equals dir of code1, dir of code2, and then we'll have our -e equals JS, HTML, whatever. So we have this error statement that gives the user some hint on how to use this. And afterwards we will panic, invalid arguments given. So now we have some very strict parsing, which means every command needs to start with a dash, then have one of those three letters equal D, either D, E, or F, and then it needs to have an equal sign. So after we've checked that the flags are syntactically correct, the next thing we should do is evaluate what is on the right-hand side of our arguments, right? So let's see, determine the individual arguments for each flag. And I just call this RHS for the right-hand side. And we'll start off with this being the characters from the third until the end, because, or this is actually the fourth character, but index 3, because everything before that will just be the descriptor of the flag. Now let's see, we'll get an iterator to this so that we can work on it. And we will collect this into a string. So now what we have is this right-hand side as a string. And because all of our arguments could theoretically have multiple expressions on the right-hand side separated by a comma. We're going to split this at the comma. And now what do we want to do with it? After we split that, so split just gives you some string views, so to say. So these are these guys. And we need to convert them back into proper strings because we want to store them in a vector of string. So what we do is we map over them, and each of those, so we'll use a lambda in this map, and you see what we're working on are string slices, and we'll do it into, which is basically our way to say, okay, we want to convert into whatever is needed, and please Rust compiler decide what we actually need. And right now the Rust compiler doesn't really know what it should be converted into, but because we have another collect statement at the end where we specify that this is going to be a vector of strings, it now knows to convert into a string. And this is possible. You can convert string slice into a string. So this is a very typical expression you would have in Rust when you're working more on the function or the functional side, function-oriented side. So you very, very often, if you have a collection, you will just call iter on it to get an iterator. And in this case, the first thing we do is collect it into a string so that we can then split the string at the comma into a lot of string slices. Then we will take those string slices, convert them back into strings, and collect it into a vector of string. Well, this is quite explicit, but on the other hand, I mean, it's basically 4 or 5 lines of code for an operation that is really rather complex, so I guess we're still good with that. And because we want to have some control over what happened and some output, we'll have a little print line here. RHS is equal to, and this is our right-hand side. So for now, let's not do more. Let's just check whether this works. So we'll call parse args config.parse args. And yeah, we will move the arguments that we get in here because we can basically consume them. There's no real need to have them around after this parse function. And in here, we'll have the args, yeah? And we can, as a first step to creating and verifying a list of all files, we will have a config, which is configuration : new, and we'll put in our args. But remember, the first argument was the path to our executable, which we don't need, which we actually can't put in there because it's not syntactically similar to what we have back here. So we'll just take a slice from the first or element with index 1 all the way to the rest. And because this is now a slice, but we expect a vector of strings, we'll have to call into again. And in order to avoid the warning right now, I'll just preface this variable with an underscore, which symbolizes the Rust compiler that yes, I'm aware of the fact that this is a variable that is not used, and I think it's okay, so please don't warn me about that. So let's check again. This is looking good. So our arguments are path to executable, -d, -e, and we'll see that those arguments are individually parsed, and we'll get this right-hand side, which is a vector of strings, .source.test, and this right-hand side for the -e argument with the file extensions is rs, js, html. That is looking stellar. So, how do we continue? Well, we have to, in some way, distinguish which of the arguments is actually being called, f, d, or e. And, well, nothing better than a match statement for that. So we'll have chars at 1, which is our letter, our character that will determine what the action is. We have a d, which would be a directory. So what we do is save directories, and we don't push back here because push is only used when you have a single argument that you want to push. So for example, if you have a vector of strings and you want to add a string at the back, you would do push. However, we know that we can have multiple directories. So what we will do is we will extend, and we will extend by RHS, right? So what this does is it takes a vector and extends it by another vector, meaning all the elements that will be in here will be individually pushed to the first vector, which is what we want here. So if we have E, this means we're working on file extensions, and we'll extend this by RHS. And if we're working on F, we're having our file names that we want to extend. And remember that this is not the whole alphabet. There's a whole lot of letters missing. We know for sure that if we have any other letter than D, E, or F, we already panicked here, which means we cannot even get to this point. However, the Rust compiler kind of disagrees and say, hey, match statements have to be exhaustive. So please provide some statement for the rest. So what we will do here is we will just say for all other cases, just continue, because we know we'll never get here, right? And this is already how we'll set up our members here in the parse step. Of course, we're not at a point where we can start parsing the files, because if the user provided them with -f, I mean, we do have all the paths to files, but we don't know whether they actually exist. And if the user provided them with -d and -e, we actually have no file at all to work on. We just have a directory that we need to search through and match the file endings. So at this point in time, we cannot start working. But we could just print our configuration, right? So some more debug statements. Config after parsing the args is gonna be a debug statement of self. And this should work rather nicely because we derived debug up here. So we have some generic default debug print statement that the compiler will provide for us. So let's see what's going on here. If we call with -d and -e, we will have in our configuration file extensions of RS, JS, and HTML, looking good. We have no file names yet. This is an empty vector. And we have the directories, which are two, which is .source and .test. So everything's looking stellar, looking good. So let's get into the nitty-gritties of finding whether those files actually exist, if they were provided with -f, or searching for them if only a directory was provided. Let's do the verify step first, okay? We'll have a member function here, which also will be private, doesn't have to be public. And it is called verify files exist. And I'll take a mutable reference to self here, because what I want to do is if I have a list of files and one of them does not exist, I want to delete this file or this entry from the list, so that when we're going to our second step, where we'll have to open the files and count the lines of code in there, we're sure that the files are actually existent. And so I want to avoid having any invalid entries in there. So this is a bit of a head scratcher at first. And I will have to admit that I spent 10-15 minutes on just writing those few lines when I first made my template for this project. Well, we're arriving at a very idiomatic, very typical problem that you often have, which is not easy to be solved, not straightforward in a lot of programming languages, which is you're iterating over some collection. In this case, it's a vector. And at the same time, you want to modify this collection. And I mean, there is a simple way around doing this, which is you're making a copy. And while you're iterating over the original vector, you will modify the copy. And therefore, you're avoiding all the problems that can turn up here. But you have to be very careful. Like if you're modifying the actual original vector while you're iterating over it, you might invalidate the iterator that is iterating over this collection, and therefore you will have some kind of undefined behavior. I mean, there's nothing good that can come from this. So the way I chose to do this here, and it looks kind of ugly, but it works, is I say, okay, I want to assign to self.filenames. And what I want to assign to it is a purged, validated version of this vector in which I know that all of the paths really exist. So what I'll do, I'll take self, and then I will get self.filenames. And on top of this, I will create an iter, which is, you know that by now, we did the same thing up here. If I want to iterate over something, I need an iterator. And now I want to filter. Filter is a very common function that you use in functional programming, which just tells, okay, if the expression that we will have here, the predicate, returns true, then keep this item in the collection. And if it returns false, then throw it out of the collection or neglect it. What we're going to be taking in is P, which is short for the path. And you can see this is a reference to a string. And I have no idea why it's that way, to be honest, but we're going to work with it. So if it does not exist, and the way to check, I mean, there's multiple ways to check whether a file exists. The way I found out that it's probably done in Rust version 1.0 and beyond is you use fs : metadata. And first you need to use, by the way, this is a really nice feature of VS Code. It will just import this using statement for you. So we need fs metadata, and we will now have our path, which is just p, and we will say is okay. So what it does, I think what it does, is it's looking up whether it can find metadata for this path and checking if the metadata is okay, so the file is not corrupted or something like this. And we only want to take action if it is not okay. So if it is not okay, we want to, again, print an error. And in this case, I'll write warning here, basically from the idea of compiler error and warning. Oh, error is, we can correct that, error. Basically, everything that is an error will lead to panic, and everything that is a warning means we can still continue, but I would just like to inform the user that something went wrong. So the file, and we'll have the file here. Let's put quotes around this. Does not exist. Skipping. And then we return false, which means that we are not gonna keep this file, and otherwise we will return true. And you can see the compiler is screaming at me already because we're not really finished with all of this, and we'll have to do some more. So what we get out here is actually a reference to a string. And we cannot overwrite a reference to a string onto a vector of actual strings, so we'll have to do some more work. In this case, we need to create strings from string references. And the way I chose to do this is I'll have a map function which just executes a function for everything that, or for every single element that we will get into here, and we will just do the into, meaning that in the collect statement afterwards, we will have to specify what we actually want. And this is a vector. And yeah, it should be S, not P. And you see now the compiler is satisfied. So what is happening here? Again, we take our vector of strings, get an iterator so we can iterate over it. Then we'll do the filter. And if we would not want to have an error warning here, we would actually be okay with just having fs metadata is okay in here. And you can leave out the curly braces, you could leave out the return statements. This would be okay, which just means if our path is okay, path to our file has metadata, then keep it, otherwise we'll neglect it. But in this case, I did want to include this warning, which means I have to make the curly braces because this is now more than one statement in this Lambda function, and therefore I need to embrace this in curly braces. Then I will give the warning and return false, otherwise I will return true. So at this point, before the map, what we have is a lot of references to strings of the original vector. Okay, so you could think of it like you have a vector of, let's say, 10 strings, and after this filter, you have references to only 8 of them, because 2 of them maybe didn't exist, and this is where we returned false here. So now you have a vector of string references, so to say, or iterators over string references, and only part of the original ones because some of them might not be a valid path. So what we do is we now create actual strings from those references, because you cannot work on the original copy while you're iterating over it, remember? So we're creating copies here, and we are collecting those copies in a vector, which is now a vector that contains only the valid string paths. And in the end, we will assign the original variable, or we will assign this vector of only the valid copies, the valid string paths, to our original variable. So we've kind of verified that all of our paths, or that the paths that are now stored in file names actually exist. Okay, bit complicated here. So it's now important to, of course, call this function. And the way I would like to do this is, we have 2 modes of operation, obviously. One is you can either provide the directories and the extensions, and the other way of operation would be you provide file names. And to be honest, it might even be sensible to combine those 2 options. Let's say you have a folder, big folder with hundreds of files in there. So you provide the directory name and the file extensions. But on top of that, you have 1 or 2 individual files that are not in this folder, but you also want to include in your line of code counting. So you provide some of them with -f. And I don't want to do work twice, which means if we first walk through the directory and get all the files that are in there, we know that we only get valid files as there because we checked for them ourselves, right? It's not user input. The files that we actually find in there are determined by our program and therefore will be valid anyways. So we don't need to check those twice. We only need to check the file names that were provided with the -f. So I first want to verify that the files exist, and then afterwards I want to parse for all the other files that are provided with the -d, -e operation mode. So there's only one thing left now in our config, which would be exactly finding all of the files that are in a directory, right? So I will call this function a very short and expressive name, which is find files in dir with extension. Well, that's not exactly a short and precise name, but it is concise, I think, meaning that it shows you through its name exactly what it's doing. So we're finding all the files in a directory with an extension, and actually we could call this recursively find files in directory with X, but I'm not going to care for that now. We know that this will be recursively. So what we need to do first is, we know that we can provide multiple directories, so we will have to iterate over all those directories. So now, of course, I could write, or we could write this algorithm ourselves for going through all of these directories. But I mean, let's make a sensible line between, okay, this makes sense to implement ourselves to learn stuff, which is like parsing of the arguments. Of course, you can find a library to do this. But I think we're getting into territory where finding all the subdirectories recursively in our operating system is not something we want to write ourselves, right? So what I would suggest is we will include a crate here, which is called walkdir, and I chose to take version 2.3.3 because at the time where I was updating, where I was thinking about this project, this was the most current version. And the way this works is, if you do something like walkdir, and we will use this, new from rootdir, we can read what this does, right? It creates a builder for a recursive directory iterator. So recursive meaning it will go into lower and lower directories until it can no longer find any. Starting at the file path root. This is what we provided, root directory. If root is a directory, then it is the first item yielded by the iterator. If root is a file, then it is the first and only item yielded by the iterator. If root is a symlink, blah, 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 blah. Okay, we don't care about symlinks. Let's keep things simple. We don't need to build an absolutely bulletproof command line tool. We just want to build something in a reasonable amount of time that works for us. So obviously, this will give us something that is iterable in some way because it needs to go through all the paths, right? So we can iterate over this, and I will just call this entry. So we get some problem here. I mean, it's not a problem. It's actually good by this crate that it will not directly give me a directory entry, but it gives me a result. Because, of course, this can lead to an error, right? For example, if you provide some directory that doesn't even exist, how are you going to get a recursive iterator over that? It's not going to happen. So the first thing we need to do is some housekeeping and some error handling. So I choose to use shadowing here, meaning that I will override this result variable with the dir entry, which is contained in case that we get an okay result, and otherwise I will just skip over this one entry and go to the next one. So we will match on the original entry, which is a result. Let's fill the match arms here. So if everything goes okay, then we have a dir entry, and we will just assign this to our entry. And if things go wrong, we'll have an error. And in this case, I first want to print an error message again. Printline. In this case, it's a warning because I think that if one of the paths is non-existent, maybe there was a typo by the user, we can still iterate over all the other paths that are valid. So I'll just give a warning here. Could not access this directory. And we will also forward the error that is given by walkdir. And in this case, we will have rootdir and the error. Additionally, we will just continue, meaning we will skip this entry in the loop and we'll go to the next one. So, and of course, we need the semicolon here after entry, because this is an assignment of a variable. So now entry is a dir entry. So we took the first step towards getting all our entries, right? And whenever we take a step somewhere that we're not really sure whether that works and what comes out, we will just have a little debug statement, current entry, and we'll just print that out. Let's see whether this works. So what we get here is, of course, nothing because we didn't really call that yet. So after we verified all the files that have been provided with the -f flag, we will then find all the files in the directory with a certain extension. Again, second try. Okay, perfect. We will see that we have the directory entry of .source, and then we have .source main.rs and .source config.rs. Those are all of our source files, and this is the folder of our source. So that seems to work, very nice. And now we need to check whether the file contains the extension that the user provided, right? We want to filter here. We don't want to have all the files. There might be some, I don't know, other assets in there, which are definitely not source files. And what we can do here is we can take our entry and get the path, which is the full path to this file. And then we can say .extension. And we will have a match on this if this works. So this will give you an option. It will either not contain anything, then it will be a none, which is understandable. For example, our source folder does not have an extension, and other files like binary files on Linux also don't have extensions. So it's understandable that this .path.extension method will give you an option, which we will see it's an option, and it either has an OS string reference in it or it has nothing in it. So we're matching on that. If it has nothing, we're not doing anything anyways. We don't need to add any files to our list, and we're only acting if we have something in there. And the thing we need to check for is whether this file extension is contained in this file extension's vector of strings. So we'll say if we don't have it, if not self.file extensions .contains. And now we have a bit of a file conversion or variable conversion to do again. What we have here is a reference to an OS string. What our file extensions are a vector, or are a vector of strings. So we'll say this extension, we convert this to a string, we unwrap it. I mean, it's not actually best practice to do a lot of unwrap, like bare unwraps in production code. Number one, this is not production code. Number two, I think there's not so much that will go wrong and can go wrong when doing the string conversion from an OS string to an actual string. So I just leave it up as a task for you, which is open, to do this in a bit of a nicer way rather than unwrapping. And we'll still have to do toString. I guess you could do into here as well to be a bit more consistent with the rest of our code. So yeah, we'll have a bit of overhead here because we're creating an actual string, so we can we can match that with strings that are in our file extensions vector. Yeah, I mean, maybe also an open task for you, right? Work with string slices here. So if this is not contained, we'll just do nothing. We'll continue. However, now we're at a point, if we arrive here, then we know that this file actually has an extension that the user wants to account for in our line of code counter. So what we do is we need this entry converted to a full path, a string. And again, this can, for whatever reasons, not work, and therefore this method gives you an option. So we'll do let sum, if let sum, and I'll call this current file name equals entry dot path, and we'll have that toString. And basically we can do, we can't do really into in here because the compiler doesn't really know what we will need, but we can do to owned. So current file name. It's still a string slice? Okay. You know what? We'll do this inside here. So what we want to do now is we want to append this path to our file names. So we'll have current file name dot, and now we can do the into here to get a string from it. And this should be it, actually. Let's look over that again. This was a bit messy, right? So we know that we can have multiple dirs by having this dirs flag set. So we'll loop over all of them. Then we'll initiate a walkdir builder at this root directory. This can result in an error, therefore, oh man, those pop-ups are annoying. So can result in an error, therefore we match on it. If we are okay, we will take the dir entry. If we are not okay, we will put a warning and omit this path. Okay. After that, we have a little bit of a debug statement. Then we will see whether we can get some extension of this path. And if this file extension contains, or if the file extensions that the user specified contains the file extension that is present with this current path, then we will do something, otherwise we will just continue. And the do something is actually, we will take the path to this file, convert it into a string slice, and then push it back as an own string into our file names. Great. This means that after this routine has run, we should have all of the files that we need to check for in our file names variable, meaning the ones that were provided with -f and the ones that we found in the directory provided by -d with file endings provided by -e. Okay, complicated, but we did it. So again, some debug output. So configs after walkdir, and we will just output ourselves again. Let's run this. Yes. Okay, perfect. This is basically what we wanted. We're first going through the source directory. We find the two files source.main and sourceconfig.rs. And we can see those in the file names down here, source main.rs, sourceconfig.rs. Then for our .test folder, which doesn't exist, we get a warning, could not access .test, and the error message is no such file or directory. Pretty obvious, yeah? Okay. So let's check some other variations now. Let's say we don't look for RS file endings. And this is how we end up with an empty file names. Perfect, that works. So let's include the RS again. What else can we check for? Yeah, we can add a file individually. For example, we want to have our cargo.toml file. So we'll say /f and -f and put cargo.toml in there. And nice, it it checked whether cargo.toml exists, and obviously it did, otherwise it would not end up in our file names down here. Now let's add a file that does not exist, cargo2.toml. And we'll have warning file cargo2.toml does not exist, skipping, and in the end we don't have it in our file names. So it looks as though everything works quite well. Surprising, amazing. And we have some rather nice high-level function up here with the new, which just creates a new configuration. Then it parses the args, it verifies that all the files exist that were given with the -f, and it finds all the files in the directories with the given extensions. And in the end, we get back our config file. So what we have left to do is the actual line of code counting and the output. So I think this video is already long enough. I'd like to split this build in two parts. The second part is going to come rather soon, but I think that reading all the configuration and finding on the files is a real nice work package that is now contained in one video, and it has a lot of similar techniques that we used. So I think this is a nice point to stop. I hope you like this new tutorial style or new video style where I built some small tools with Rust. If so, I can definitely go on and build a few more tools. Also leave some suggestions of what tools you would like to see built, or where in my code you think there might be errors, there might be some options for improvement. If you learned something, if you enjoyed the video, please like it. As I said, leave a comment. And if you really liked it, you can also consider subscribing. So my name is Max, this was Green Tea Coding. I hope to see you next time.